All right, in this second video, I'd like to illustrate the expenditure minimization problem. So, the expenditure minimization problem provides us a different angle from which we can analyze the consumer's behavior. Okay, so the statement of the problem is right here. So the consumer chooses one bundle X and then must be feasible. Okay. Now the objective function is different. And so P dot X stands for the expenditure necessary for choosing bundle X given price factor P. Okay. Now the constraint is given by this. So U of X is higher than U. Okay. We usually call that U or the target utility, right? So the interpretation of expenditure minimization problem is like this. So the consumer wants to achieve and list this level of utility, the target utility. Now, what is the way to minimize the expenditure for achieving this level of utility? Right? Now, what consumption bundle he has to choose? Right? So that is a description of the expenditure minimization problem. And once again, that provides us a different angle from which we analyze the consumer's behavior. So this is usually called the dual structure, the dual problem to the UMP, utility maximization problem, in the following sense. So if we think about the EMP, right? So in order to capture this constraint, right? Then we have to fix one indifference curve. Its level is given by the target utility U. So that is a set of bundles giving the level of utility U to the consumer. Okay. All right. So the consumer wants to achieve and list this level of utility, right? So for doing that, for this purpose, the consumer has to choose one bundle inside this region, right? The upper contour set of this level U, right? And then now we pin down one indifference curve here, okay? And then we adjust a budget line, yeah? Because as the if we set the minimum expenditure for achieving this level of utility, that gives us a one budget line here, yeah? And then we adjust the height of this budget line, up or down, yeah? And to see that what is the most efficient way in the sense that consumer can achieve the level of utility U at the minimal cost. It gives us the basic idea of EMP. All right. So there is a very close relationship between the problems UMP and EMP. In the UMP, we fixed one budget line. Okay, because in the description of UMP, we know we can observe the price factor and we can observe the wealth, right? And then that gives us the exact one budget line, right? And then we adjust the level of utility, right? So we can think of several indifference curve. So at which bundle the consumer utility is indeed maximized. So that is a UMP. Given budget line, what is the highest level of utility attainable? All right. Now we interchange the lower of constraint and the lower of the objective function. So we interchange the objective function and the constraint. Okay? So the constraint in the UMP was this expenditure. It's concerned about expenditure, right? Expenditure cannot exceed the consumer's wealth, right? And the U of X was the objective function in the UMP, right? Now we switch them. So now we, U of X, consumer's utility appears in the constraint, and the P dot X, expenditure now appears in the objective function, all right? So now we pin down one indifference curve and adjust the level of expenditure, yeah, figuring out the most efficient way of achieving that, the cheapest way of achieving the level of utility. Okay? So that is a EMP. So in this sense, the EMP is often referred to as the dual problem of the UMP. Yeah. All right. So here is the I wrote down the basic difference between these two, and UMP computes the maximum level of utility that can be obtained given worth W. On the other hand, EMP computes the minimum level of wealth required to reach utility level U. Okay. Once again, the basic idea is switching the constraint and the objective function, right? And that is often referred to as a dual problem in mathematics. There's something about the dual structure. EMP can be thought of as a dual problem to the UMP. You can learn way more by taking math econ class in graduate school. Yeah. All right. So the way to solve this EMP is exactly the same as before. So we adopt the Lagrangian multiply method to tackle this problem, right? But the way to write the Lagrangian is slightly different because the UMP was a maximization problem. Yeah. But this EMP is a minimization problem. So we have to manipulate the Lagrangian slightly, and the way to manipulate the Lagrangian is now we have to first put the objective function. So p dot x appears first, okay, right? And then we need a lambda Lagrangian multiplier, and the way to convert the constraint is the same as before. Yeah, we change the constraint. Something is larger than 0. Okay, because we have u of x on the left and u on the right, target utility. So we move this target utility to the left hand side. Yeah, then u of x minus u is going to be larger than 0. Right? So we change the constraint to this form, okay, and then multiply by lambda. Okay, and the only thing we have to do for a minimization problem is we change the sign of this lambda. Okay, previously it was a plus in case of UMP, but in case of minimization problem, we put the negative sign in front. Okay, so that is the only way we have to do for minimization. That is simple. Okay. All right, then the previous Lagrangian multiply method can be applied to this minimization. So if we have an interior solution, so the demand for each commodity is strictly positive, then we have a solution. So suppose that we have a candidate for a solution for the EMP, right? Then this candidate must be a stationary point of this Lagrangian given some non-negative lambda, and plus we have a complementary Slangness condition. So lambda times this guy, so the second term of this Lagrangian must be equal to 0. All right, and then but if we pay attention to the stationary point condition, then we are gonna have the partial derivative of this Lagrangian with respect to every commodity is going to be 0 at this stationary point. All right, so for example, if we take the partial with respect to x sub L, then p dot x gives us p sub L, the price of a good L, because this is just a linear equation, and the partial with respect to x sub L, so partial of the second term, gives us the lambda times marginal utility from good L. So we take this and set it equal to 0 for every L. All right, so in case of two commodities, the stationary point condition gives us two equations. So P1 minus lambda derivative with respect to x1 is equal to 0. So marginal utility from good 1 is equal to 0, and P2 minus lambda times marginal utility from good 2. Okay. So just as we did before, we can combine these two. Two conditions using vector form. So now lambda times gradient of u, yeah, so the collection of these two derivatives equals price vector p. Okay, so the only difference is comparing with the previous condition. Now, in case of a UMP, we have a Lagrangian multiplier on the right. Okay, but in case of EMP, we have a multiplier on the left. Okay? So, geometrically, we can offer the same interpretation. Okay, the direction in which the utility function is increasing the fastest, right? So that is the gradient, and the price factor indicate the same direction, right? All right, pretty cool. Yeah. And so, in the next slide, we have one example. Once again, Cobb-Douglas utility, and so if we want to find a solution, to EMP, all right, then we can set up the Lagrangian like this. L depends on x1 and x2 and lambda. Okay, because now we are working with the two commodities, and we first write the expenditure function. So p1 x1 plus p2 x2. That is what we are going to minimize, right? And minus lambda. Now, given this utility, x1 alpha times x2 to the power 1 minus alpha. Okay? And minus target utility u. Yeah. All right. So the way to find the solution is we take the partial derivative with respect to x1, and you're gonna have p1 minus alpha equal to 0, and partial with respect to x2 gives me p2 minus lambda. Now we have 1 minus alpha minus alpha. Yeah. So in this computation, I just took one away from the power. Yeah. Here from x1 and here from x2. Cool. Then all right, so the easiest way to solve these two equations is we can divide the first equation by the second, right? Then p1 will be divided by p2, so p1 over p2. Okay, then if we take the ratio of these second terms, then lambda will be cancelled, okay? And alpha over 1 minus alpha, and x1 alpha will be cancelled by this one. Okay, so we are left with just x1. On the bottom is x1 to the power negative 1, right? And x2 to the power negative alpha will be cancelled by this guy. And then we are left with just 1 x2 on the top. Okay. So this way, we can derive the relationship between x1 and x2, and finally, so one thing you guys have to be careful is, for doing this operation, so for dividing the first equation by the second, we need a condition about the lambda. Yeah, we know p1 and p2 are strictly positive. Okay, because we are working with a some, so we excluded out free goods. Okay? So the price of every commodity is strictly positive. Right, so that is okay. P1 over P2 is well defined because we know P1 and P2 are strictly positive. Okay, but if we take the ratio, so if we take the ratio of the second terms, we have to make sure, you know, these are non-zero numbers, right? Otherwise, you know, this ratio will be undefined. Yeah. So we have to make assumption about the lambda strictly positive. Yeah. Lambda strictly positive. Yeah. So by the complementary slackness condition, if lambda is strictly positive, because the product of these two should be equal to 0. Yeah. So this guy, okay, the expression in the bracket should be equal to 0 at the optimum. Yeah. That is the implication of this positive sign. So we have additional equation equals u, target utility, right? So using these two equations, you can solve for x1. So you can find the x1 and x2 and express them as a function of p, price factor, p1 and p2, and the target utility. Okay? So here's a solution. Right? So the solutions to the E and P are called compensated or Hicksian demand. Yeah? And in Musgrave and Winston Green is denoted by letter H. Okay? So H sub 1 stands for the Hicksian demand for good 1. H sub 2 demand for good 2. Okay? And then if I use a bold letter H, okay, that is a collection of these two. Yeah? And remember, this Hicksian demand depends on price factor P. As a given price, the consumer wants to minimize expenditure, right? And also depends on U, right? Because he attempts to achieve at least this level of utility. Okay? All right. So Hicksian demand is a function of P and U. Right? So if we compare Hicksian demand, so we are going to compare this Hicksian demand with Wallachian demand. That is actually can be thought of as the key essence of consumer theory, classic consumer theory. But one notable difference is Wallachian demand function depends on P and W. X star depends on P and W. Both are observable. P and W, price factor, and W are observable, right? But U, or the target utility, is not observable by the analyst, right? So the one disadvantage of the Hicksian demand is it depends on unobservable parameter, right? But there are, you know, bunch of advantage of so there are a bunch of advantages regarding this Hicksian demand. So this is why we separate EMP from UMP, and this is why we have to study this Hicksian demand. Okay, it turns out that, you know, Hicksian demand is used you know, in many applications. So the reason is, if we know something about unobservable characteristic, and we can do you know, more accurate computation for example, welfare change. Yeah? For example, the Korean government decides to subsidize people due to the outbreak of COVID-19. Now, how much subsidy they need, okay, for, you know, maintaining their consumers' well-being, yeah, maintaining the national people's well-being. And that is a very, you know, important question for the government. But if we have exact information about this unobservable well-being utility, okay, then we can derive the more accurate. So we can do more accurate computation for, you know, the necessary subsidy for the national people. Okay, and so on. Okay, so we are going to discuss several you know, applications regarding this Hicksian demand in the next week. All right. So as of now, the only thing we have to know is, you know, Hicksian demand is a solution to the expenditure minimization problem, right? And so if we found a solution, Hicksian demand, and we go back to expenditure, yeah, so we found a solution to this EMP, okay, so Hicksian demand for good 1 and good 2, okay, you know, in case of 2 goods, we have this one. That is what we want to minimize. Okay, and we found a solution for x1 and solution for x2. Okay, and if we substitute this optimal solution, okay, Hicksian demand, into this expenditure, okay, then this gives us P1 H1 P2 H2. All right, and this is called expenditure function. Okay, so it can be regarded as the value function from the expenditure minimization problem. Right, so instead of x1, we substitute Hicksian demand for good 1, and instead of x2, substitute Hicksian demand for good 2. Okay, right, and as the Hicksian demands depend on price factor and u, so expenditure function also depends on these two parameters. Okay, so it tells us expenditure function tells us the minimum expenditures necessary to achieve the target utility u given market price p. All right, so I'm going to talk about some properties of this function, and turns out that function e possesses the following properties. First, it is homogeneous of degree 1 in the price factor. Right? The reason is, okay, think about the E and P. So the homogeneous of degree 1 in P, that means if we scale up price factor by T, okay, so here T is a positive constant, right? Then we can pull out this T and put it in front like this. Okay? So in general, I'm not sure if I talked about this, but we say function f is homogeneous or homogeneous of degree k. Okay? If we scale up x, the argument of this function f by alpha, okay, then it gives us alpha to the power k f of x. All right? So that's the definition of homogeneity of degree k. All right, and then there is one important equation regarding this homogeneity, right? So that is called Euler's equation. Euler's equation, and this is frequently used in the analysis of consumer and producer behavior. So let me briefly mention about this right now. The Euler's equation tells us if function f is homogeneous of degree k, then we have the following property. Which is, the gradient of f dot x, okay, the dot product of the gradient of function f and the vector x is going to be k times f of x. Okay? So for example, if the function f depends on two variables, x1 and x2, then gradient of f is going to be partial with respect to x1 and the partial with respect to x2, and vector x is x1 and x2, which is k times f of x1 and x2, right? So we can rewrite this using the definition of the dot product. So usually we express this partial derivative by f sub 1 and f sub 2. Okay, so here the subscript stands for the partial derivative with respect to the argument. Right, then we have f sub 1 times x1 plus f sub 2 times x2. Remember the definition of the dot product between two vectors, yeah, is the sum of the component y's products, like this. Okay, so we have this on the left, okay, and the right we have k times the original function. Okay, so this is called the Euler equations. And the way to derive this equation is we take the derivative, this definition, key characteristic of homogeneity with respect to alpha. Yeah? Then by the chain rule, after derivative, so if we take the derivative of this function f evaluated at alpha x with respect to alpha, and we're gonna have gradient of f dot x, okay, evaluated at alpha x by the chain rule. Okay, because gradient is the derivative of the outer function, and x is the derivative of the inner function alpha times x, and whose derivative is just x, right? And the right hand side, the derivative is k alpha to the power k minus 1 times f of x. All right, and then substitute 1 for alpha, gives us this guy, right? So 1 to the power k minus 1, no matter what k, we have this. All right, so consequently, so if expenditure function is homogeneous of degree k or degree 1 in price vector p, then we have this property. Gradient of E with respect to P, okay, times P, that gives us the original expenditure function. All right, cool. Okay, so why the expenditure function is homogeneous of degree 1 in the price vector? Because think about the structure of E and P. In E and P, we minimize P dot x given this constraint, right? And the value function of this optimization is going to be E P comma U, right? And if we think about E T P comma U, right? So that is minimization TP dot x subject to the same constraint. All right, so for solving this minimization problem, because T is a scalar multiple, right? So we can disregard this T for a second, right? And solving the the original minimization problem, right? And after that we can multiply the constant T. Okay? So ETP is going to be T times E of P. Okay? So that is a homogeneous of degree 1. Okay? And then the second property is the E function is increasing in U. Right? That is quite intuitive, nothing to prove. If the target utility gets higher and higher, the consumer is willing to achieve a higher level of utility, he needs more money, right? So he has to expand a little bit more. So expenditure function, the value of expenditure function is strictly increasing in U. Yeah, as increasing in this argument, right? And there's a non-decreasing in price, right? So intuitively, if the price level is increasing, right? He wants to achieve the target utility U, right? Then the minimum expenditure necessary for this objective gets higher and higher, right? And the way to see this, the way to prove that is, all right, so we have to show that. So let me prove this, just a second property, non-decreasing in the price vector, right? So we have to show that, let me here. Right, so suppose that we have two price vectors, P and P prime, and P is higher than P prime. Okay? So the price of every commodity in price vector P is higher than, in price vector P prime. Cool. Then we show that, we needed to show that E of P comma U is larger than or equal to E of P prime U. Okay? Then we say, we can say function E is a non-decreasing in price vector P. All right, and then think about this. So E of P comma U, E of P comma U is a Hicks, so the dot product between the price vector P and the Hicksian demand. So in case of two commodities, can be written as P1 H1, P2 H2. You know what? Let me first work on this expenditure function when price vector is P prime. So in case of P prime, by definition of expenditure function, that is the dot product between P prime and H prime, and H prime is the Hicksian demand under price vector P prime and target utility U. Okay? So that gives me this. Am I right? All right. Then we know that P is higher than P prime. Okay. So P1 prime. So we can write this way. Because P1 prime is lower than P1, and P2 prime is lower than P2. Okay. Because E is higher than P prime. Vector P is higher than vector P prime. All right, and then the H1 prime is the Hicksian demand when the price vector is a P1 prime. Okay, so there's some bundle. The most efficient way to minimize the expenditure when price vector is P prime. Okay, that is not necessarily equal to the most efficient bundle, the cost minimizing bundle, when price vector is given by P. Okay, so we can say P1 H1 plus P2 H2. So H1 and H2, those are Hicksian demand when price vector is P. Okay, so there's a definite. So this inequality holds by the definition of Hicksian demand. Okay, it tells us the most efficient, the cost minimizing way for obtaining the target utility U. Yeah. Cool. So that is the definition of expenditure function under price vector P. So we proved that. Yeah. So we proved the fact that expenditure function is non-decreasing in the price vector. Okay. So I think this is doable. And the third property of expenditure function is the next. Function is concave in the price vector. Okay? And remember the definition of a concave function. So if the function is concave in P, then the function's value at the average is going to be larger than or equal to the average of function's value. Yeah? So in general, we say function f is concave if f of alpha x plus 1 minus alpha x prime. Yeah? So that can be interpreted as the function's value at the average bundle. Okay? That is larger than or equal to the average of function's value, alpha times f of x and 1 minus alpha times f of x prime. Yeah. All right, and then it can be shown that expenditure function has a concavity structure with respect to price factor. All right, so before proving this, let me first prove this. All right, so the basic idea of this inequality comes from the fact that, remember, expenditure function is a value function from minimization problem. Okay, so this is a minimal expenditure. Okay? And on the left hand side, we have just one minimal expenditure function. On the other hand, on the right hand side, we have two minimal expenditure functions. Yeah? So comparing these two, because we minimize twice, yeah, for each price factor on the right hand side. Yeah? So consequently, we have a larger quantity on the left. Right? So the way to prove this is, so let me call this average price, weighted price by P star. Yeah? So by definition of expenditure function, we know that this equals P star dot Hicksian demand. Yeah? Hicksian demand. All right, and then because P star is the average price, so we can rewrite this alpha P dot H star plus 1 minus alpha P prime dot H star. Okay? And by definition of Hicksian demand, let me call the Hicksian demand H under price factor P and H prime under P prime. Okay, so we can see that alpha P dot H, okay, that is a minimal expenditure under price factor P. So that quantity will be smaller than this one. Okay, and by the same reasoning, P prime dot H prime is a smaller quantity than this one. Okay. By the definition of the Hicksian demand. Okay. So this is alpha times E of P and 1 minus alpha times E of P prime. Okay. So we have the desired inequality. And the more important thing is the interpretation. Okay, so if we think about intuitively why expenditure function has to be concave in price, right? So in case of two goods, okay, then expenditure function is P1 times H1 plus P2 times H2. Okay? And remember, H1 and H2 both are functions of prices. All right, so here we fix P1 and U. Okay, so holding the other variables constant. Yeah, Ceteris paribus assumption. So holding P1 and U constant. Yeah, we change P2 only. Yeah. Then concavity of E, function E, implies that the graph of the E function looks like this. It is concave downward like this. Yeah? So if we draw the supporting line, the tangent line at P2 bar, yeah? So the graph of the function should be below this supporting line. And that's the implication of concave function, right? Right. So this expenditure function tells us at P2 bar. So when P2 equals P2 bar, yeah, in order to attain U, the consumer has to expend at least this amount of money. All right, and then we draw the tangent line here. So because this tangent line meets the expenditure curve at this point. All right, so the equation of this line segment is going to be P1 times H1 P1 and P2 bar U. Okay? So Hicksian demand for good 1 when the price of good 1 is P1 and price of good 2 is given by P2 bar, okay, and U, and P2 times H2, the same argument, P1, P2 bar, and U. Okay? Because we already fixed P1 and U, this is a constant. Okay, this is a constant. All right. So so this is a linear equation. So we change the value of this P2 only, right? Where H1 and H2, so the demand schedules are fixed. Okay, so they were optimal demand schedules, the cost minimizing demand schedules when price factor is given by P1 and P2 bar. Right? So concave expenditure function means, right, comparing with this line segment, right? When the price of a good changes from P2 bar, okay, by adjusting H1 and H2, consumer can effectively reduce down the expenditure further. Okay, comparing with this one, in this line segment, the demand schedules are fixed. H1 and H2 are fixed. Okay, we change only this P2, right? But if we allow the consumer to change so they respond to a price change, okay, so he's allowed to change H1 and H2. That is what happens in the expenditure function, right? So then consumer can effectively reduce down the expenditure. So that is why expenditure function is concave, and that is why expenditure function appears below this line segment. All right. Cool. And then the next property is a Shepard lemma. So it tells us, the partial derivative of an expenditure function with respect to PL, the price of a good L, indicates the Hicksian demand for that good. Okay. So in case of two goods, expenditure function, the derivative of expenditure function with respect to P1 gives us Hicksian demand for good 1. With respect to P2, gives us Hicksian demand for good 2. Okay, so that provides us a convenient way to cover discover the Hicksian demand from the expenditure function. So if we are informed about the expenditure function, okay, we know the minimum expenditure, minimum expenditure necessary for target utility. Okay, then the only thing we have to do to find the Hicksian demand is to simply take the derivative, right? So that is the main implication by we can obtain from Shepard lemma, right? And the way to prove this, okay, so this result is immediate from the envelope theorem. So yeah, I'm going to talk a little bit more about envelope theorem in the supplementary video, because this is a very important theorem in not just the classic economics but a modern economics. but in modern economics. So I'm going to talk a little bit more about envelope theorem in the separate video, but the basic idea of envelope theorem is, suppose that we want to maximize some function. Say we want to maximize the following quadratic function plus tx plus 5. Okay, so here t, you can take this t as a key parameter, right? And then we want to maximize this single variable function with respect to x. So we want to choose. So we want to see where this function is minimized, okay, over x. Then the way to find a minimum or maximum point. I'm sorry, did I say minimized? Oh, it should be maximized because we have a negative sign in front of the highest power. So so we take the derivative, right, and set it equal to 0. So x is t over 2. Okay, so the function will be maximized at t over 2. Okay, so because this is a concave function, concave downward. So if we put in t over 2 for x in the objective function, then we can obtain the value function, the maximal value for each parameter value t. So let me call that v of t. So the maximum value, the function we can obtain from substitution, and that is going to be minus t over 2 squared plus t times t over 2 plus 5. Right, so it's going to be t squared over 4 plus 5. Okay, and in many applications we are interested in the derivative of this function v. So how does the optimal value respond to change in the parameter? Okay, so that is a v prime of t. So from this, in this example, v prime can be easily obtained from taking derivative of this guy, that is t over 2. Okay. All right, and then the envelope theorem is really useful because it offers a shortcut of finding this responsiveness of the value function. Right, so the theorem tells us the only thing we have to do to find this derivative, the derivative of the value function with respect to parameter, we take the objective function, right, and then take the derivative with respect to t. Okay, with respect to t, then we have just the x. All right, because a x squared is constant, 5 is a constant, tx's derivative is just x, right? And then we substitute, we plug in the optimal solution for x, that is t over 2. Okay? So way more simple, right, than taking these steps. Right? We don't have to go through this computation, okay, by virtue of this envelope theorem, right? So think about the minimum EMP, E1 times x1, E2 times x2. All right, and then we are interested in how does the expenditure function respond to change in price, right? And then, for example, change in P1, right? And the only thing we have to do for this job, we take the derivative of the objective function with respect to P1, then we are left with just x1, okay? And then we substitute the optimal solution. So the solution to this minimization was a Hicksian demand. So there's a H1. Okay? So that is a one way to prove this Shepard lemma, right? Using the envelope theorem. Cool. So I'm going to explain this in the supplementary video, right? So I have to go to the seminar right now. So let me stop the video in a second. Video right here, and then continue to record the remaining. So continue to record the video for the remaining part, right?